So, um, if you walk into a modern arena today, or maybe one of those sweeping new transit hubs, or a massive contemporary museum, you aren't actually standing inside a traditional building.
Right, you're really not.
You are basically standing inside a frozen algorithm. Because for roughly 4,000 years, the physical world around us was, well, it was completely dictated by the limitations of the human wrist.
Yeah, whatever an architect could physically draw with a straight edge and a compass, that was exactly what we could physically build.
Exactly. But today, that constraint has been completely wiped out, which
Which
is
it
wild.
is totally wild. I mean, we are looking at a fundamental rupture in how physical space is even conceived. I think we have to look at the severe friction of the analog past
Oh,
first.
absolutely. The dark ages of drafting.
Right, because historically, the tools themselves impose this massive invisible ceiling on creativity. For centuries, architecture relied on measured plans, descriptive geometry, physical models. Drawing a complex building by hand is just a grueling, sequential process.
It sounds exhausting. I mean, making a single change to a hand-drawn blueprint wasn't just a minor annoyance, right? It was, well, it was an economically punitive disaster.
A complete disaster. If you made a mistake or the client wanted a change, you were literally scraping ink off vellum with a razor blade.
Hmm.
Or starting completely over.
Which forced this huge psychological barrier against risk. Like if an architect wanted to design a facade with 1,000 entirely unique, slightly varying curved windows.
They couldn't. I mean, the sheer labor required to manually draft the geometry for each individual pane of glass would bankrupt the firm before they even broke ground.
Right. So all that symmetry, the typological repetition, those rigid grids we associate with older buildings, they weren't just aesthetic choices, they were survival mechanisms for the draftsman.
Exactly. And that physical constraint naturally separated representation from fabrication. A blueprint was essentially just a picture of a building.
Just a set of instructions.
Right, a static set of instructions handed off to a builder. It was not the building itself. Which brings us to the introduction of computer-aided design, or CAD, in the late 20th century.
But looking at the texts, early CAD was essentially a conceptual plateau, wasn't it? Like, it digitized the drafting table, swapping graphite for pixels, but it didn't really change the underlying paradigm.
No, it didn't.
It's kind of akin to giving a novelist a faster typewriter. Like, it speeds up the mechanical act of typing, but it doesn't help them invent a better plot. The architect was still operating with an analog mindset, just staring at a monitor instead of paper.
That's a perfect analogy. It lacked computational intelligence. But it did introduce one foundational revolution, which was the psychological safety of version control.
The age of the undo button.
Yes, the ability to iterate infinitely without the penalty of destroying a master vellum draft. That fundamentally altered the architect's risk profile. It compressed time and allowed for this massive new tolerance for experimentation.
Okay, so if CAD was really just a faster pencil, there has to be a distinct threshold where the computer stops being this passive canvas and actually starts acting as an active co-pilot.
Right, absolutely.
Like if I'm an architect and I stop manually drawing lines and instead I start plugging in mathematical rules to see what the software spits out, I'm not really designing a building anymore. I'm designing an engine that generates a building.
That is the exact line where the digital turn truly begins. The shift from representation to generation.
Generation. Wow.
Yeah, the computer is no longer just recording a form the architect already imagined in their head. It is actively using computational logic to produce a form that the architect might never have anticipated.
It is wild.
It really is. Architecture suddenly enters into these deep dialogues with cybernetics, systems theory, ecology, and data structures.
And the text highlights parametric design as the main engine behind this, which, to try and simplify it, if you think about a complex three-dimensional spreadsheet, you start to understand the mechanism.
Oh, the Excel analogy is great for this.
Right. So in Excel, if you link 50 cells to a single variable and you change that one input, it automatically updates every single formula across the whole board.
Yeah.
Parametric design is that exact same logic, just applied to physical geometry.
Exactly. So instead of drawing a fixed window, you establish a parameter rule set. You dictate that the window's, say, louver angle must adjust based on the specific solar orientation of the building's latitude.
Well,
So if the site location changes or that sun angle variable is tweaked even slightly, the entire three-dimensional geometry of the facade mathematically morphs and ripples to accommodate the new data.
that is mind-blowing. So the final physical object is entirely secondary to the network of dependencies you've created in the software.
Precisely. And this marks the death of the modernist rule of standard repetition. The The architect Patrick Schumacher heavily championed this, calling parametricism the defining style of our network society.
Parametricism. Got it. And you see this vividly in the work of architects like Zaha Hadid, right?
Oh, absolutely. Zaha Hadid's work is the quintessential example.
Her buildings aren't composed of static, sharp-angled boxes at all. They're these fluid, continuous gradients. The spaces flow and adapt, behaving much more like, I don't know, a biological cell or a geological formation than a traditional building.
Yeah, it replaces isolated zones with continuous differentiation. It's beautiful. But this incredible complexity introduces a profound logistical bottleneck.
Oh, I bet.
Because if architecture is now this massive interconnected system of data, physics, and changing variables, a traditional 2D floor plan is entirely useless. You cannot hand a contractor a flat piece of paper and ask them to build a liquid-looking honeycomb structure.
Right, an architect can't just be sketching on a screen anymore.
Yeah.
Because if you have a billion data points tied to a physical space, like the structural load of some non-standard curve, the routing of the ductwork, the exact solar heat gain on a piece of warped glass, you have to be building a literal one-to-one database before you even think about pouring concrete.
You absolutely do. And this is where the concept of virtuality comes in.
Virtuality, like virtual reality.
Well, in this context, virtuality doesn't mean putting on a VR headset to look at some marketing rendering. It means the building is rigorously lived in digitally before it ever exists physically.
Oh, I see.
Software platforms like Revit, Rhino, and Maya facilitate what we call building information modeling, or BIM. They turn the architecture into a hyper-dense, multidimensional database.
Which fundamentally cures one of the oldest nightmares of the construction site.
Yeah.
Because historically, you would have, like, the electrician and the plumber getting into a literal screaming match on a job site because the flat 2D blueprint lied to them.
Oh, all the time.
And suddenly an HVAC duct is crashing directly into a structural steel beam. Resolving those physical clashes in the middle of construction costs millions of dollars.
Millions. And BIM predicts and eliminates that friction months in advance. The digital twin literally simulates the physical reality. It tests sunlight and shadow behavior, acoustic responses, structural stress under dynamic wind loads. And it even tracks the supply chain and future maintenance schedules. It forces this hyper-collaborative environment that blurs the traditional boundaries between the architect, the structural engineer, and the fabricator.
See, it feels like a paradox to me.
Yeah.
Because the architect is essentially curating a massive database now, functioning almost as a systems manager. Does that take the art out of it? Are they just data managers?
That's a common critique, but actually outsourcing the complex math to a machine is exactly what grants them the freedom to dream up structures that look visually impossible.
Because the software proves it won't fall down.
Exactly. Because the software perfectly simulates the physics, they have the absolute mathematical proof that their crazy topological fold or swarm-like roof won't instantly collapse.
Okay, so that mathematical confidence is crucial. But surely that leads directly to the physical bottleneck of the whole process, because an algorithm can easily spit out a digital design where absolutely no two panels or beams or structural joints are exactly alike. But human hands cannot physically measure, cut, and weld 10,000 totally unique steel nodes on a dusty construction site with that level of precision.
They really can't. Which means we have to bypass the human hand almost entirely. If the digital file contains the exact geometric coordinates for every single unique piece, you don't print a blueprint.
What do you do?
You send the file directly to the machine that is going to cut the steel.
Directly to the machine. So that gap is bridged by digital fabrication.
Yes. We move from the digital file directly to the physical form. Techniques like CNC milling, laser cutting, large-scale 3D printing, and robotic assembly. They take the algorithmic data and translate it into direct physical actions.
And this flips the entire economic model of the 20th century on its head. Because industrialization was entirely predicated on mass production, right? Stamping out 1,000 identical parts on an assembly line to drive down the cost per unit.
Exactly. Economies of scale.
But a computer numerical control, a CNC machine, it doesn't have a bias for a straight line. It is literally just reading X, Y, and Z coordinate data.
That's the secret right there. Cutting a completely unique, complex curve costs the exact same amount of computational effort and machine time as cutting a rigid, straight line.
Which is the defining mechanism of mass customization. Like getting a tailor-made suit for the exact wind and light conditions of a specific street corner generated at an industrial scale.
Mass customization is a huge shift. Fabricating 1,000 uniquely shaped, mathematically distinct facade panels is now just as economically viable as fabricating 1,000 identical squares. The machine does not care about the complexity of the shape, it simply follows the path.
And the aesthetic results of this are radically different from anything built in previous centuries. Space becomes about these continuous information streams.
Very much so.
The essay actually notes that this new architecture looks like data in motion,
Well,
physically reflecting our globalized, hyper-networked culture. So we see the rise of blobs, folds, fields, swarms, and lattices replacing the traditional post and beam grid.
we do. But, visual culture has a tendency to hijack this kind of technological leap. The ability to generate these sweeping photorealistic renderings means that buildings are increasingly consumed as pure image.
As viral spectacle on a screen, long before a shovel ever hits the dirt.
It absolutely becomes an arms race of imagery. Competitions for major civic projects or corporate headquarters are frequently won based on the seductive quality of the rendering alone.
Wow.
And spectacle becomes a central part of the architectural value, which carries heavy risks when those algorithmic dreams actually collide with the physical world.
Right, because a perfectly smooth, mathematically flawless digital model doesn't account for the absolute messiness of reality. A construction site isn't smooth. It rains. Steel warps. Joints leak. The source specifically calls out the myth of seamlessness.
Yes, the myth of seamlessness is huge here. Digital architecture inherently celebrates friction-free continuity. But physical architecture is bound by gravity, harsh weather, intensive manual labor, and the realities of ongoing maintenance.
It's physical.
Exactly. A highly polished digital rendering often papers over brutal real-world construction conflicts, or worse, it completely ignores the local cultural context of the neighborhood it's being dropped into.
Oh, that's a great point. And there is also the reality of the person actually standing inside the space. Like, if a building is perfectly optimized by an AI, let's say it's a new transit hub, and the pedestrian flow is mathematically 100% efficient, and the structural load requires the absolute minimum amount of steel.
Right.
But if the resulting space feels deeply alienating, cold, and entirely out of scale to a human being, didn't the algorithm fundamentally fail its occupants?
This raises such an important question. Computational capability does not automatically guarantee architectural depth. We are seeing a profound tension between elite spectacle and actual public utility.
Yeah, totally.
A multi-billion-dollar corporation might use these insanely expensive proprietary software tools to brand themselves with a fluid, hyper-modern headquarters. But we have to ask if that complexity actually serves the public life of the street level, or if it is merely an exercise in corporate vanity.
And that leads to a glaring paradox regarding sustainability, doesn't it?
Yeah.
You might utilize a supercomputer to run millions of iterative simulations just to save 10% on a building's HVAC energy consumption.
Right, which sounds great on paper.
But you just spent an astronomical amount of carbon and physical resources fabricating the highly bespoke, intensely complex structural gymnastics required to hold up that wavy parametric roof.
It requires a very delicate balance. Digital tools are incredible at optimizing daylight, reducing raw material waste during fabrication, and simulating efficient airflow. But as the text emphasizes, digital intelligence must be paired with social and ecological intelligence.
It has to have a grounding.
Exactly. The author notes that without those grounding human elements, the algorithm merely creates a glittering maze with no moral compass.
A glittering maze with no moral compass. Wow. That perfectly captures the stakes of this shift. We didn't just give architects a shinier set of drafting tools. The digital turn expanded the entire epistemology of how we build.
It really did.
The physical geometries are unprecedented. The fabrication relies on mass customization rather than mass production. And the underlying theory values interconnected living systems over static, isolated objects.
We have entirely reconnected the act of representation to the act of making, and that connection is mediated entirely by data.
So the next time you walk into a sweeping, hypermodern transit hub or a museum that looks like a liquid wave frozen in time, look closely at the intersecting panels and the curved steel. You aren't just standing in a room. You are inhabiting a physical data set.
It's exactly what it is.
And as artificial intelligence increasingly steps in to optimize every single variable of our physical environment, perfecting the structural math, the internal temperature, the ambient lighting, it leaves us with one incredibly provocative question from the text's conclusion.
Right. As our physical spaces become functionally flawless, generated and maintained by perfectly rational algorithms, what distinct human fingerprint remains?
Will we eventually find ourselves longing for buildings with a little bit of analog friction? Like, will we actually miss the physical flaws, the rigid constraints, and the dumb, static nature of a brick wall, when every structure around us is a perfectly optimized predictive machine?
It's entirely possible.
Definitely something to mull over the next time you step out your front door.